Welcome to this lesson on graphing rational functions. After this lesson, you will be able to determine the characteristics of rational functions and then use them to graph. There are a variety of characteristics that help us graph rational functions. This is the list of characteristics that will be the most helpful to us. One of the main characteristics of rational functions is that there can be holes. A rational function has a hole when a factor from the numerator cancels with a factor in the denominator. Let's consider this rational function. Notice the factor of x minus 3 in the numerator and denominator cancel each other out. So we know that there will be a hole located at 3. The hole is located at 3 because 3 is the value that makes the factor equal 0, 3 minus 3. We can then use the simplified function to further investigate this. After canceling the x minus 3, our simplified function is 1 over x plus 1. So we know the hole is at 3, but let's find the y value of the hole. We will take the 3 and substitute it into the simplified function. 1 over 3 plus 1 gives us 1/4. So the hole is located exactly at 3, 1/4, which you can see in the graph. Vertical asymptotes are also other important characteristics of rational functions. Vertical asymptotes occur at the x values that make the denominator equal to 0. So let's take a look at this example. In the denominator, we have two factors, x plus 3 and x minus 2. Neither of those cancel out, so we will have two vertical asymptotes at the values that make them equal to 0. So x equals negative 3 and x equals 2. Those two values make the denominator equal to 0. So we have two vertical asymptotes located at those. Along with vertical asymptotes are horizontal asymptotes. Horizontal asymptotes are a little bit more complicated. If the degree in the denominator is larger, or you can think of this as bottom heavy, the horizontal asymptote will always be at y equals 0. So if we consider this example and the degree in the numerator and denominator, we have that the degree in the numerator after canceling is 0 because there is nothing left there except the 1 placeholder. The degree in the denominator is 1 because there is still a single x to the first power. So our asymptote will automatically be at y equals 0. Another scenario is if the degree in the denominator and the numerator are equal. Then the horizontal asymptote is at another constant, y equals c. So if we look at this scenario, the factor of x plus 3 in the numerator and the factor of x minus 1 in the denominator have the same degree. Both of them have a degree of 1, or the first power. So our leading coefficient of 3 in the front tells us that our asymptote will be at y equals 3. And then there's one final scenario. If the degree in the numerator is larger, or you can think of this as top-heavy, then the horizontal asymptote is actually oblique or slanted, and it will be in the form of y equals ax plus b. We will learn about this later in another lesson. Finally, another characteristic is about x and y intercepts. Let's recall what an x-intercept is. An x-intercept is where a graph crosses the x-axis. So let's take a look at this x-intercept. An x-intercept occurs when the function is equal to 0. So we can use the idea of setting the numerator equal to 0 and solving for x to find it. Similarly, the y-intercept occurs where the graph crosses the y-axis. So we will substitute 0 in for x and then solve for y. It is important to note that not all of these functions have both x and y intercepts. So now that we have all those ideas in mind, let's think about how rational functions are built. Let's write a rational function that could match this graph below. Let's start with the characteristics we notice. First, we see that there is a vertical asymptote at x equals -2. So we know that the denominator must have a factor of x plus 2, because -2 would make it equal to 0. Another characteristic we see is that there is a hole at 3. So we know that the numerator and denominator both had a factor of x minus 3 that would cancel out, and substituting in 3 would make it equal 0. Next, we see there's an x-intercept at -1. So this comes from our numerator. There must be a factor of x plus 1, because -1 would make it equal 0. Finally, we see that there is a horizontal asymptote at +4, so we must have a leading coefficient of 4 in the numerator. All of these ideas together allow us to graph rational functions as well as write the equations for them, like we did here. Now let's spend some time graphing. Here's our first example. F of x equals 3 times x minus 4 over x minus 2. We know that our domain is all real numbers except for 2, because 2 would make the denominator equal to 0. We also know that there are not any holes because none of the factors cancel out. Speaking of the 2 in the denominator, we know that the vertical asymptote must be 2. X equals 2 because 2 made the denominator equal to 0. We know the horizontal asymptote must be at y equals 3 because the degree in the numerator and denominator is both 1 and our coefficient is 3. Now let's talk about our intercepts. Let's substitute 0 in for x and solve. We find the value of 6. So we have a y-intercept of 0, 6. Lastly is our x-intercept. Let's set the numerator equal to 0. So our x-intercept is 4. Now we can sketch in the remaining curves. And we've graphed the rational function. Let's take a look at another example that is a little more complicated. F of x equals x plus 2 over x plus 2 multiplied with x minus 3. Starting with our domain again, this time there are 2 values. But we have to be careful because we notice that x plus 2 and x plus 2 cancel out, but we still must consider them when we find the rest of these characteristics. But the simplified function is also helpful. So our domain is all real numbers except -2 and 3. Although the x plus 2 factors canceled out, we must consider that when we work through the rest of this problem. Now speaking of the factors of x plus 2, that tells us that we must have a hole at -2. But now we need the y-coordinate. So let's substitute -2 back into the simplified function. We find that it's -2, -1/5. The remaining factor in the denominator gives us our vertical asymptote. X equals 3, because 3 makes it equal 0. This time, our horizontal asymptote is at 0, because the degree in the denominator is greater. The degree in the denominator is 1, and the degree in the numerator is 0, because we do not see any x terms there anymore. Finally, our intercepts. Let's substitute in 0 to the simplified function. So we have a y-intercept of 0, -1/3. Finally, let's find the x-intercept. Let's set it equal to 0. But wait, we have a problem. We can't set the numerator equal to 0 because there are no x terms left. So remember, it is possible to not always have an intercept. So we can sketch in the left side of the graph. However, we do not have a point on the right side of the graph. It may be necessary to pick a test value to determine where the curve will be. You could substitute in the values of 4, 5, 6, 7, etc. to determine if the result is positive or negative. If we substitute any of those values in, the answer is positive. So the graph must be above the axis. Finally, one more example that's a little different from the rest. Take a look at this function. We notice that the factors of x minus 3 will cancel out. And this is our simplified function. Notice the simplified function doesn't look rational anymore. So with our domain, it's all real numbers except for 3, because 3 makes the denominator equal to 0. Even though it canceled out, it must be considered. So we know we actually will have a hole at 3. So let's substitute the 3 back in to find exactly where the hole is. 3, negative 8 is our hole. Because there is no remaining factor in the denominator, there will be no vertical asymptote. Because our function is no longer rational, there will not be a horizontal asymptote either. Finally, we have our intercepts. Let's substitute in 0 for x. So we have a y-intercept of 0, negative 2. And finally, we can set the function equal to 0 to find the x-intercept. Negative 1, 0. Notice when we graph this function, and because of the lack of asymptotes, we ended up with a linear function, but the linear function has a hole. After these variety of examples, it is important to recognize that rational functions can be very complex, and one graph can look very different from the next. There can be multiple vertical asymptotes, holes or no holes, and the horizontal asymptote can be at different values depending on the relationship between the numerator and denominator. We will continue to learn more about rational functions in later lessons.